All right, in this video, we're going to talk about suggested homework problems from 9.1. This starts our discussion of sequences and series, which is our third major component of calculus of a single variable. The first component was limits and derivatives. The second component was antiderivatives and integration. And the third component here is sequences and series. We'll also have a component coming up in chapter 10 to talk about parametric and polar equations and calculus with parametric and polar equations. And we'll get into how that relates to conic sections and things like that, which is almost just like an introduction to calculus 3. You need to stop thinking only in terms of X and Y and things like that. So anyways, let's go ahead and talk about what a sequence is. We'll be talking about sequences in 9.1, just so we can get to a definition about a series in 9.2 that involves the word sequence. But really, sequences are nothing more than functions whose domain is the natural numbers. If you forget what a natural number is, the natural numbers are the set of counting numbers 1, 2, 3, 4, so on and so forth. We sometimes will define our sequence to, or our series, usually to start at 0 with the whole numbers instead. And that's 0, 1, 2, 3, so on and so forth. They're the same size. They're both countable infinities. And they have a one-to-one correspondence here where I could just transform the function and shift it and not have a problem here, because 0 would map to 1, 1 would map to 2, 2 would map to 3, 3 would map to 4. So anything defined for the whole numbers can be defined for the natural numbers, and that's not going to be a problem for us. So now let's talk about what it means for a sequence to converge. So a sequence converges if the limit as n approaches infinity of the nth term of the sequence that we denote by a sub n equals a finite limit L. The limit exists if limit of n goes to infinity of a sub n does not exist. The sequence diverges. So it's very similar to how we use the word converge and the word diverge with integrals towards the end of chapter 8. And we wanted to know if that integral, especially that improper integral in 8.8, converged or diverged. And it converged if it added up to be a finite number L. It diverged if it went to infinity or negative infinity, or we couldn't tell what it did because it didn't add up to any finite number L. So same kind of idea here. So let's go ahead and talk now about an important idea called a recursive sequence with problem number 1. And this is going to be awesome for those of you who are computer science people. You're going to already know the word recursive because of recursive algorithms. So what does it mean for a sequence to be defined recursively? So a sequence is defined recursively when an, the nth term of the sequence, is calculated with previous terms in the sequence that we're going to denote by something like a sub n minus 1, a sub n minus 2, so on and so forth. A sub n minus 1, a sub n minus 2. The base terms or basis terms of the recursive sequence must be included in the definition. So what do I mean by that? So I have to have enough information to get started. Let's talk about a common recursive sequence here, the Fibonacci sequence, which says that any term in the Fibonacci sequence is the sum of the previous two terms in the Fibonacci sequence, but I have to tell you that the first two terms in the sequence are 1. Then I can start calculating that, okay, if I want F3, that's going to be F2 plus F1, because 3 minus 1 is 2 and 3 minus 2 is 1. And I have F2 and F1 to say 1 plus 1 is 2. So Fibonacci sequence is 1, 1, 2, and then I can keep going here. The F4 would be F3 plus F2 would be 2 plus 1 is 3, and so on. And you can see that if I add the two previous terms, I get the next term. But I have to tell you what to start with here to have the Fibonacci sequence. And I should call that sequence of F sub n's. All right, enough on that. Let's look at 3 here. Which function grows faster as n approaches infinity, and explain? So question 3, we have f of n is an exponential function, 7 to the n. G of n is equal to n minus 1 factorial. So far, we haven't really done much with factorials. We'll do a lot with factorials in this chapter. Factorials actually grow faster than exponential functions. Exponential functions were one of the fastest growing functions that we knew about in our library of functions right now. Now, factorial functions are going to grow even faster than that, because this has a constant multiple of 7 to generate the next term. This one is increasing. The more terms that I have as I'm going to infinity, this multiplier is getting larger and larger all the way out towards basically infinity. So this is going to grow much faster. So G of n grows faster than F sub n in general. There are some exceptions to this, but in general, factorial functions grow faster than exponential functions. And they definitely do as n approaches infinity. But we could have some places between 0 and 1, or where the exponential function may actually be growing faster. Or you just have to be careful with these things. I said between 0 and 1, and that can't happen. But with some of the smaller numbers. So remember, n has to be a natural number, so you can't just replace it with x in your calculator and draw a continuous function for these things. That's not really the correct way to do this. You're going to want to be in sequence mode in your calculator. So you're going to want to change modes here to sequence, and that's going to give you a sequence of dots that are not connected. So let me show you here that this is 7 to the n right here, and I really don't need, I don't think I need first case here, but I'll give it to the calculator that this is going to be n min is 1, and my sequence of n is what I want. I can also do a sequence of n plus 1 or a sequence of n plus 2. And this is 7 to the 1 will be 7. Let me graph this. And so you can see that there's 1, 7. 249 is off of my graph there, but you can see if I zoom out some more, we'll start to see the exponential curve there as I would grow, and it's just the sequence of dots. I think that's going to be important for you to realize that these are discrete and not continuous functions that we're talking about in this section. Let's look at number 9. Nine says a sub n is equal to, this will be something we'll talk about later. It's alternating here. This is an alternating sequence, that this -1 to the n or -1 to the n plus 1 is going to make the signs change on every term of the sequence. So write the first 5 terms. We want a1 is equal to -1 to the 1 plus 1. 2 over 1 is -1 squared times 2 is 1 times 2 is 2. A2 is -1 to the 3rd over 2 thirds will be a -2 thirds. A3 is -1 to the 4th times 2 over 4 is a +1/2. A4 is a -1 to the 5th times 2/5 will be a -2/5. A5 will be a -1 to the 6th, 2 over 6, so that will be a +1/3. So now at number 13. A sub n is equal to 10 over n plus 1. Match the sequence with the given nth term. The graph, graphs are labeled A, B, C, and D below. So if I look at the limit of a sub n as n goes to infinity here. That's going to go towards 0. It's going to be positive and decreasing, related to the graph of 1 over n plus 1. So it would look something like 10 here, and at 1, this is going to be 5, and then keep going down like this. It's exponent. It's a rational function that gets closer and closer to this. We don't really have this piece of the graph over here because those aren't natural numbers, but if you wanted to imagine this piece of the rational function here, if you graphed, let's go back to our function mode, 10 over x plus 1, and zoom 6. And I'm drawing this connected, but we really know that it doesn't have all these pieces there. Like I was saying, that it's just at 2, this is 10/3, and then at 3, it's 10/4, and at 4, it's 2, and so on. So it looks like this rational function that's approaching that asymptote, but it's really just that sequence of dots like we were just talking about. If I switch back into sequence mode, you'll see that here of 10 divided by n plus 1, and go to this is 1, 10 divided by n plus 1, and the first term here is 10. See, there it is. That's what it looks like. First term here would actually be 5. There we go. So which one does that match? That matches with C. All right, let's look at 15. -1 to the n, and we'll be starting at -1 and graph, and you see that it just bounces back and forth and back and forth, and that's what D does. N is equal to a -1 to the n. Just be at 1, we're at -1, at 2, we're at 1, at 3, we're at -1, at 4, we're at 1, at 5, we're at -1, so on and so forth. Okay. Let's look at number 17, and we're going to reduce some factorials here. So you're always going to take the bigger down to the smaller by multiplying out the first few terms until you get down to the same place as the smaller factorial, and then they will cancel out. N times n plus 1 is n squared plus n. Let's look now at 29. Says to determine convergence or divergence, 5 over n plus 2, limit as n goes to infinity of an is equal to limit as n goes to infinity, 5 over n plus 2 goes to 0, so it converges because it goes to a finite number. 33, an equals 3n plus root n over 4n, limit as n goes to infinity of an is equal to limit as n goes to infinity of 3n plus root n over 4n. I'm going to divide everything by n. Limit as n goes to infinity of 3 plus n to the negative 1/2 over 4 equals 3 plus 0 over 4 equals 3/4. So that converges because it has a finite limit. Let's look at 35. Limit as n goes, let's start with the definition. An is equal to ln of n cubed over 2n, which is equal to 3 ln of n over 2n. So limit as n goes to infinity of an is equal to limit as n goes to infinity of 3 ln of n over 2n. I didn't talk about this earlier, but we were talking about which function grows faster, because that's really what L'Hopital's rule is telling us about. So ln of n grows slower than the linear function n, but we can use L'Hopital's rule here because this is going to approach infinity over infinity. So limit as n approaches infinity of 3 over n over 2. Let's call that 3/2 divided by 2 so that the over n doesn't look like an ln. So that's equal to 3 over n divided by 2 is 3 over 2n. That's what I was trying to write there. And this will be this limit as n goes to infinity of 3 over 2n. So that is equal to 0, and it converges. Let's look at 39. 39 is an interesting one because I need to really put a restriction on this that the book forgot to state. So an is equal to n to the p over e to the n, and they tell me that p needs to be greater than 0, but also n needs to be greater than 2 here. I don't want 0 and I don't want 1 because 0's not very fun because 0 to any power is going to be 0. 1's not very fun because 1 to any power is 1. So we don't want those cases here, but we want to consider. We know that it converges for n equals 0 and for n equals 1. We're interested about when n is big, right? So limit as n goes to infinity of an is equal to limit as n goes to infinity of n p to the p over e to the n. All right, so n's getting huge here. And p is, it really doesn't matter how big n is, though. It's a constant here, and I'm sorry, it's our variable here. It's like x, and it's like x is going to infinity, and this p is some constant. It's big, but it's a constant, so it doesn't matter whether it is x squared, x cubed, x to the fourth. P is some power, right? So eventually, if I take enough derivatives, then the derivative of the top is going to stop going to infinity and it's going to go to a constant. But e to the n down here is always going to go towards infinity because exponentials keep coming back as exponentials keep coming back as exponentials with L'Hopital's rule. So because the exponential function in the denominator grows faster than the power function, this is called a power function in the numerator, this is going to go towards 0. And so it converges. I hope all that makes sense. I can't really show you L'Hopital's rule an infinite number of times here because we don't really know how big P is, but I could give you some examples for however big P is, and that if P was 3, if I took 4 derivatives, I'd get, or if I took three derivatives, I'd have a constant, and I'd have a constant over infinity, which would go to 0 if n was 100, if I took, or p was 100, if I took 100 derivatives, I'd have a constant over infinity, and it would go to 0, so on and so forth. So let's look at 43. 43 is kind of interesting because it requires the squeeze theorem. A n is equal to sine n over n. Limit as n goes to infinity of a n is equal to limit as n goes to infinity of sine n over n. Well, I know that whatever this L is needs to be between limit as n goes to infinity of -1 over n and limit as n goes to infinity of 1 over n, and L is between 0 and 0, so L has to be 0. '55. One of the things we're going to learn about sequences in this section is about monotonic sequences, which would be non-increasing or non-decreasing sequences. We really like them when they're always increasing or always decreasing. So I've got some different ways to find that out. I'll show you how I will solve this problem. It's a little different than how the book solves this problem, but I'm going to look at this as f of n. And I'm going to look for, is it always increasing or always decreasing here? Or does it change sign from increasing to decreasing? So I'm going to look at the derivative here. Now, your teacher may not want you to do it this way. Your teacher may want you to do a direct comparison, and I'll see if I can show you how to do that in just a second. So, but let's use the product rule here. So the derivative of the first part would be 1 times the second part plus, leave the first part alone, take the derivative of the second part. I'm going to factor out a -1/2 e to the -n over 2. And that's going to give me n minus 2 as the other piece. I know that n has to start at 1 here. and it looks like there's a critical number at 2. So if I look at numbers between 1 and 2, even though there aren't really any numbers that are allowed to be between 1 and 2, I just want to see what is happening from 1 to 2, whether it's increasing or decreasing. Then this is going to be a this is always positive, so this can be a negative times a negative will be positive, and it will be increasing from 1 to 2. And then from 2 to infinity, this is a negative times a positive will be a negative and decreasing. So the book is going to actually start listing out the first few terms and see that it goes up and then it comes back down and it'll stop. I don't like this method because you don't know how far out here your critical number is. You could have it at 100 or 1,000 or something like that, and you're going to be tempted to just list out the first few terms and say, oh, it looks like it's always doing the same thing. I prefer that you actually do something to solve to see that, whether that's with the derivative or whether you use some kind of direct comparison. So let's, now that we know how far we need to go, just find A1 is 1 times e to the negative 1/2 is e to the negative 1/2. So e to the negative 1/2 is approximately 0.6065. A2 is equal to 2 e to the negative 1. So 2 e to the negative 1 is equal to approximately 0.7358. And then A3 is 3 e to the negative 3/2. And this is going to go back down to 0.6694 approximately. So see that this is increasing and then decreasing, so not monotonic. It's not non-increasing or non-decreasing here, but it is bounded because we can see that once I hit A of 2, A sub 2, it's always going to be decreasing. So there's a local maximum, which is actually going to be an absolute maximum. At n equals 2. And that's going to be A2 we have is 0.7358. So I can write that as the magnitude of the nth term is always going to be less than or equal to A2, which is equal to 2 over E exactly, which is approximately 0.7358. So it is bounded. It's bounded above. All right, let's see if I can show you this idea of what an plus 1 is equal to n plus 1 times e to the negative n plus 1 divided by 2. And occasionally we can compare this to by dividing by, say, an, which was ne to the negative n over 2, and see if this is a bigger number divided by a smaller number, then it's going to be greater than 1. If it is a smaller number divided by a bigger number, it's going to be something less than 1. And we can take the, we can see what that's going to do here, that this is n plus 1 over n e to the negative n over 2 plus 1 over 2 plus n over 2 will be n plus 1 over n e to the 1/2. And this piece right here is greater than 1 when n plus 1 over n e to the 1/2. I want to see where it's greater than 1, where it's less than 1. And I can solve that with my calculator and see where that's true and where it's less than 1. And I'll see that it comes out with the sine rules basically right here, that it switches at 2. So this is going to be increasing on 1 to 2, and then decreasing from 2 to infinity. It's really the same thing, but this requires you to stick some stuff into the calculator and graph it. We'll do some things with some direct comparisons later that will be usually a little better than this, but I just wanted to show you that some teachers don't like you taking derivatives. I think derivatives are awesome. I think that's why we focused on derivatives so much before this, and that we should take the path of least resistance. If that's a direct comparison, we should do that. If that is a derivative, we should do that. So let's look at 73, which is the sequence of values in the form of the nth root of n, and we want to find the first 6 values here. So this will be 1, this will be the square root of 2, this will be the cube root of 3, this will be the 4th root of 4, this will be the 5th root of 5, this will be the 6th root of 6. So let's come here, y equals, and this is going to be n to the 1 over n, and start with 1 and go to my table, and 1, 2, 3, 4, 5, 6. Just to get the decimal approximations, this is exactly 1. This is 1.4142. This is 1.4422. This is 1.4142. These two things are exactly the same. 1.3797. This is 1.348. And so now how are we going to find the limit of this sequence to see if it converges? Well, we're going to take the limit as n goes to infinity of an, and that's going to be limit as n goes to infinity of n to the 1 over n. And I'm going to assume that this converges right now and call this L. And this is going to be an infinity to the 0 situation, which is an indeterminate form, but we're not quite ready to use L'Hopital's rule. We have to use logarithmic differentiation here. So ln of L is equal to limit as n goes to infinity of ln of n to the 1 over n. So ln of L is equal to limit as n goes to infinity of ln of n over n, which is going to go towards infinity over infinity. So ln of L is equal to, by L'Hopital's rule, limit as n goes to infinity of 1 over n over 1 is just 1 over n, which is equal to 0. So L is equal to e to the 0, which is equal to 1. So limit as n goes to infinity of the nth root of n is equal to 1. Hold that 1 in your back pocket to come back and use it later. For something in the chapter, it will be important for you to know that the limit as n goes to infinity of the nth root of n is equal to 1. All right, that's it for this video. We'll come back next time to talk about suggested homework problems from 9.2, where we'll talk more about series and convergence of series. This was sequences. We're going to move on and talk about series. So see you for the next video.